Hello everyone. Today we are going to discuss another numerical related to centrifugal pump. So let's start. A centrifugal pump having outer diameter equal to 2 times the inner diameter and running at 1000 rpm works against a total head of 40 meter. The velocity of flow through the impeller is constant and equal to 2.5 meter per second. The vanes are set back at an angle of 40 degree at outlet. If the outer diameter of the impeller is 500 mm and width at outlet is 50 mm, determine A part vane angle at inlet, B part work done by the impeller on the water per second, C part manometric efficiency. The figure shows the velocity triangle diagrams at inlet and outlet. This V1 represents the absolute velocity of the water at inlet. This U1 represents the tangential velocity of the impeller at inlet. And this VR1 represents the relative velocity at the inlet. Theta is the vane angle at inlet. Now, this V2 represents the absolute velocity of the water at the outlet. VF2 represents the velocity of flow at outlet. VW2 represents the velocity of whirl at outlet. U2 represents the tangential velocity of the impeller at outlet. The VR2 represents the relative velocity at the outlet, and this phi represents the vane angle at outlet. Now, as per the data given in the numerical, the speed n is equal to 1000 rpm. The value of head hm is given as 40 meter. The velocity of flow is constant and is equal to 2.5 meter per second. So velocity of flow at inlet Vf1 is equal to velocity of flow at outlet Vf2 is equal to 2.5 meter per second. Outer diameter of the impeller D2 is given as 500 millimeter, which is equal to 0.5 meter. It is also given that outer diameter is equal to 2 times of the inner diameter. Now if inner diameter of the impeller is considered as D1, then as per the given condition, outer diameter D2 is equal to 2 times of D1. So D1 is equal to D2 divided by 2. So it is equal to 0.5 by 2 is equal to 0.25 meter. So the value of D1 is now 0.25 meter. Width at the outlet B2 is given as 50 millimeter, which is equal to 0.05 meter. Now the tangential velocity at the inlet can be calculated by using the formula U1 is equal to pi d1 n by 60, which is equal to pi into 0.25 into 1000 divided by 60, which is equal to 13.09 meter per second. Similarly, the tangential velocity at the outlet can be calculated by using the formula U2 is equal to pi d2 n by 60. So it is equal to pi into 0.5 into 1000 divided by 60, which is equal to 26.18 meter per second. Now we have to observe the velocity triangle at inlet. Now this is the velocity triangle at inlet. In this diagram we can observe that tan theta is equal to Vf1 divided by U1. The value of Vf1 is given as 2.5 meter per second and the value of U1 we have already calculated as 13.09 meter per second. So we can easily calculate the value of tan theta, and hence we can also calculate the value of theta, which is the vane angle at inlet. So tan theta is equal to Vf1 divided by U1. Vf1 is 2.5 meter per second and U1 is 13.09 meter per second. So tan theta is equal to 2.5 divided by 13.09, which is equal to 0.191, and we get the value of theta as tan 0.81 degree or tan degree 48 minutes. So we can say that the vane angle at the inlet is tan degree 48 minutes. In B part, we have to calculate the work done by the impeller on water per second. We know that the formula for work done by the impeller on water per second is given by W by G into VW2 into U2. Now this W is equal to density into acceleration due to gravity into discharge. So the work done by the impeller on water per second is given by rho into G into Q divided by G multiplied by VW2 into U2. So it is equal to rho into Q into VW2 into U2. Now we have the value of rho, we have the value of U2, but we do not have the value of Q and VW2. So we have to calculate the value of Q and VW2. To calculate the value of VW2, we have to observe the velocity triangle at outlet. So let's observe it. This is the velocity triangle at outlet. In this diagram, we can observe that tan phi is equal to Vf2 divided by this. And this is equal to U2 minus VW2. So we can say tan phi is equal to Vf2 divided by U2 minus VW2. So tan phi is equal to Vf2 divided by U2 minus VW2. Vf2 is already given as 2.5 meter per second and U2 we have already calculated as 26.18 meter per second, and phi is given as 40 degree. So tan 40 degree is equal to 2.5 divided by 26.18 minus VW2. From this we get the value of VW2 as 23.2 meter per second. The work done by the impeller on water per second is given as rho into Q into VW2 into U2. Still we have to calculate the value of Q. We know that this discharge Q is given by pi d2 into b2 into vf2. The value of d2 is given as 0.5 meter, value of b2 is given as 0.05 meter, and the value of vf2 is given as 2.5 meter per second. The discharge Q is equal to pi into 0.50 into 0.05 into 2.5. So the value of Q is equal to 0.1963 meter cube per second. So the work done by the impeller on water per second is equal to rho into Q into VW2 into U2 is equal to 1000 into 0.1963 into 23.2 into 26.18, which is equal to 119227.9 Newton meter per second. Now in part C, we have to calculate the manometric efficiency. We know that the manometric efficiency is given by GHM divided by VW2 into U2. We have already calculated the value of VW2 as 23.2 meter per second, and already we have calculated the value of U2 also as 26.18 meter per second. Value of HM is already given 40 meter. So the manometric efficiency is equal to 9.81 into 40 divided by 23.2 into 26.18, which is equal to 0.646. So manometric efficiency is equal to 64.6%. This is all for today. Thanks for watching this video.